Well, thank you all for making it back from lunch. It would appear that our session chair, Haley Sapers, may not have made it. So I will go ahead and introduce myself. I'm Maggie Osburn from Northwestern University. And today I'm excited to tell you about some recent work the Life Underground Astrobiology team has been doing to look at the subsurface biosphere, particularly that under the Black Hills of South Dakota. Excellent. So the deep subsurface biosphere consists of those organisms living in pore fluids, within deep crystalline fracture networks, and within the rocks themselves of the continental and marine crust. This talk is going to be focused primarily on the continental deep subsurface biosphere because that's where our site is. We know a fair amount about the subsurface biosphere in general, and we know that it is large, containing a large volume of organic carbon, equaling biospheres equal to that of various phases of the surficial environment in stages of Earth history. We know that that biosphere is physically and taxonomically diverse. There's a large number of processes happening, and that does seem to vary depending on where you're at. We know that those processes are metabolically dependent on the chemistry and the geology of the environments in which they're found. And this feature in particular makes these sites key extraterrestrial targets and key extraterrestrial analogs, particularly when we're looking at rocky planetary bodies such as the subsurface of Mars. We access the deep subsurface in a number of ways. In particular, we look at it in the form of springs, where we have upwelling of these deep fracture networks onto the surface. Springs are great because you can go to the edge of said springs, perform your experiments, and you can have ready and continuous access. The downside, of course, is that there's a superficial biosphere that's interacting and deconvolving the end members between the surface and the deep subsurface biospheres can be challenging, getting that subsurface end member. We also access the deep subsurface in boreholes, and in the next 3 talks of this session, you'll be hearing about CHROMA, which is a Borehole Microbial Observatory. These are great because they can go very deep, actually our deepest end member of the deep subsurface biosphere. They are easily accessible at the surface, but the challenge can be in the mixing as you go down, and with casing materials, and with influx of material or fluids from the sides. There's also diameter limits, as everything has to go down a little hole. The last, and the one I'll be talking about mostly today, is the deep subsurface biosphere accessed through mines. Mines are great because humans actually go down and can access the deep subsurface biosphere as it intersects on those levels in particular. Miners are great at taking material from the surface and bringing it down, and vice versa, and therefore bringing experimental apparatus is not a problem. They are dynamic systems, so many mines are continually being excavated, and therefore intersection of new fractures and waters that have been sequestered for millions or even billions. I see Barbara Sherwood-Lawler in the background there, billions of years. So we have some very deep fluids being accessed. There are, of course, cons. So mines influence the local hydrology. Mines produce a fair amount of contamination, and mines do tend to backfill themselves with ore, so things can be transient, which can be a problem. So today I'm going to tell you about the Deep Mine Microbial Observatory, which is a microbial observatory that I've established in the former Home State gold mine. This is a set of 6 boreholes ranging from 800 to 4,850 feet, or a little less than 1.5 kilometers. They were drilled between 1910 and 2005 and mostly capped subsequently after their drilling. And we have now adapted these sites for continuous sampling and installation of long-term monitoring and cultivation apparatus. So the rest of this talk I'll be talking about demo. The Sanford Underground Research Laboratory is in the former Home State gold mine, so it's now a science facility aimed at understanding mostly particle physics applications, but the facility does foster and encourage all types of scientific research there, so it's a science facility. This is a view of the open cut of the former Home State mine. You can see a variety of geology moving forward. These rocks are Paleoproterozoic in age, primarily metasediments, ranging in the oldest from the Yates, which is a basaltic unit, through the Poorman, Homestake, and Ellison formations, and then cross-cut by these visually striking tertiary intrusive rocks. So we have a variety of geology. The metamorphic grades range from green schist to amphibolite in a variety of windows, which contributes to the mineralogical diversity. We have water ages that are significantly younger, ranging from something like a year to extending to 10 to maybe tens of thousands of years at the oldest. So the Life Underground team has been sampling these sites since 2013. And we've taken many samples, mostly of opportunity, that look something like this. So we have fluid coming out of the wall and creating these luxuriant, slimy biofilms on the surface. And sometimes you have water actually shooting out of the wall at relatively high pressure. These sites were great, but as you can imagine, getting a controlled sample of something like this can be a challenge. What is actually happening in this photo, this one, we have a borehole that was drilled and then capped with concrete. And so the sites that we were sampling are places where this concrete cap was leaking, allowing some of this to come out. So the goal of the establishment of DeMMO was to clean this out and then interface between the subsurface environment and the mine environment in a way that we could go back and take the same samples over and over again and really start to perform controlled experiments within this subsurface environment. So we did just that, and so conveniently, many of the surf staff are old miners that are well versed at drilling holes in crystalline bedrock. And thus, this is a guy named Fritz, and he drilled out a couple of holes for us. These were sites that had been sampled previously, and thus we were able to sort of focus our efforts on the sites that were most interesting. Aha. So in our newly cleaned out holes, we placed custom designed and fabricated high-density plastic packers. Metal is the common thing to make a packer out of, but in the subsurface environment, it corrodes extremely rapidly, and thus that was not a good choice for us. The packer is composed of a threaded core and then outer components that, when compressed, seal against the wall of that borehole. And this is not advancing very well, but okay. This is the final product here. So in this way, we can actually seal that subsurface environment from the mine environment and can take real samples with time. Do you have another one? I mean, I assure you I'm pushing the button. All right. All right, so here is a cross-sectional view of the mine ranging from surface topography at the top with horizontal layers representing the mining levels. In gray are mined out ore bodies of various stages of the mining, and the arcuate colored curves are the trajectories of the diamond boreholes that we have capped, color-coded by geology. So our shallowest site, DeMMO 1, starts out here, and its borehole trajectory, while not on this map, almost outcrops at the surface. So this is by far our shallowest sample, sort of closer to a terrestrial end member, or surficial end member. DeMMO 2 is also on the 800-foot level, but accesses more diverse lithologies and somewhat older water. DeMMO 3 is on the 2,000-foot level, and you can see is heading off kind of in its own direction here. DeMMO 4 is on the 4,100-foot level. It's this green line here. And its sort of paired hole is DeMMO 5 on the 48-foot level. And you can see that these two borehole trajectories are coming into a similar package of rocks. And so these two boreholes are encountering sort of similar water with depth. The final hole is DeMMO 6, which we've not switched out and still has a stainless steel manifold, but this is accessing some interesting geology and chemistry, and thus we have kept it in the suite. Before, during, and after drilling, we've embarked on a campaign of constant monitoring of these sites. So we are currently engaged in every other month. We go and take a full suite of samples. This includes geochemistry, major anions, cations, gas geochemistry, redox-sensitive geochemistry, your physical measurements like flow rate, and also microbiology, so things like cell counts and sequencing. This is my field. go back. This is my field lead, Brittany Kruger, without which none of this would be possible, and my grad student, Caitlin Kazar, who will be speaking more on this on Friday. Just to show you a little bit of data from our suite, this is a schematic of the DeMMO network, and I'll show a couple data graphs like this. We have flow rates ranging from mostly a couple hundred mils per minute up to greater than 10 liters per minute. We have temperature that broadly increases as you go downward, ranging from 10 to about 35. pH also increases as you go downward. Oxidation reduction potential, we're getting more reducing with depth, and we're also getting somewhat saltier, maxing out at something like brackish. In terms of the number of cells in these waters, we are at low 10 to the third up to mid 10 to the fifth cells per mil, so quite low. At the top, we have very simple morphologies, mostly just coccoid cells there. Slightly more diverse in DeMMO 2, increased types of morphologies in DeMMO 3 and 4, although still very low cell densities. We get quite a lot more morphological diversity when you get into DeMMO 5 and DeMMO 6. You can see these filaments and rods in addition to the cocci, hinting at a potentially more diverse ecosystem. In DOC, we have a decreasing gradient from the surface to deep, potentially thinking about long-term carbon usage within the crust. DIC is a little interesting, so this probably is varying based on the interactions with rocks, and then the isotopes of DIC are showing potentially some closed system carbon cycling behavior. These numbers are much lower than you might expect. Just a little bit of microbiology before I run out of time. So each box is a site, and then this is data with time, so DeMMO 1, youngest, oldest. You can see, and the arrows represent where we drilled. So this is before drilling and after drilling, before drilling and after drilling. The first sort of broad scale observation is that the drilling didn't completely disrupt these ecosystems in the way you might have expected. These bars are not radically different colors from this time step to this time step. We just have a minor change in population. We have lots of unknowns. We have lots of candidate phyla, and these samples are dominated by proteobacteria, as you might expect of the subsurface biosphere. We have mostly not a lot of archaea, except we have populations in DeMMO 4, so there seems to be a local favorite. We have large populations of OP3, particularly in DeMMO 1. DeMMO 6 is very different. It's dominated by firmicutes, Bacteroidetes, and OP1. Just a little bit on ongoing experimentation. Now that we have this network, we can actually install cultivation reactors and experimentation in situ and leave it for months. And so what my lab has been doing are experiments that look like this. We call these flow-through cultivation reactors. We're changing the substrates and the minerals that are in these, allowing colonization to happen over the scale of months. Experiments in the orphan lab are testing things like lithology and flow rates, and in the ORCUT labs, we're doing controlled amendments. There are also in situ electrode cultivation reactors being done by Annie Rowe in Mo Al-Najjar's lab. Just want to plug my student Caitlin's talk Friday at 3. She will tell you more about the cultivation happening from these flow-through cartridges and show some truly beautiful images. And with that, I would like to acknowledge my funding from NASA, the SURF staff that makes these samples possible, the rest of the NAI team, and the Northwestern Stable Isotope Facility for producing our carbon isotope numbers. And I think I have 1 minute and 23 for a question.
So we have time for one question. If the next speaker can come up and get mic'd while the question's going on.
That was perfect then. You understand everything. Oh, okay.
Just a comment or two of requesting one or two
Sure.
on logistically, how difficult was it to do this work? How much effort did you require to get the equipment down? Was it difficult to work in the mines? Things like that.
So the SURF facility was extremely cooperative with our efforts. So it did take a fair amount of time and logistical planning. In terms of the transportation and the actual drilling, those were technically complicated and were met with a variety of, partial success and failures. We went through lots of drill bits and that kind of thing. But we had great cooperation from the facility in terms of actually implementing this plan. It's sort of like a government lab. It's a lot of paperwork anytime you want to do anything. But once you get permission, it goes pretty smoothly.
All right, thank you.
Thank
So
you.
Move on to the next speaker.